Okay, let's talk about another way to use rectangular coordinates while dealing with curvilinear motion. And another common idea is applying this to motion of a particle. So say you have a particle with some initial velocity. Well, this initial velocity can be broken down into two components. You can have your y velocity, initial velocity, and your x initial velocity. Now, the location of this particle, your initial location, can be a y0 with your initial x location as x0. Now, as your particle travels through space, it is acted on by acceleration, and that produces this curved path, and your particle ends up in another position over here. Actually, let's put it right there. We don't need two dots. And essentially, you have a final velocity, which, let's do the same colors, which can be broken up into a horizontal velocity, or velocity in the x direction, and a velocity in the y direction. So how are we going to deal with the kinematics here? Well, it's the same way that we learned earlier. We have a constant acceleration, and it's a vertical acceleration in the negative direction, but we can say then that dv dt equals a or since we're dealing with components that are going to be scalars in the x and the y direction, we can look at this in terms of direction. So we can look at, like, say, the y direction, and we can do our separation of variables, and we'll go from v0y to v0 final. Acceleration is constant, so we'll pull it out. We'll go from t equals 0 to our final t, or t dt, and this will result in the relationship. So our final velocity in the y direction will be our initial velocity in the y direction plus acceleration times time. Then using dy dt equals v, we'll set up this integration, which will follow again this result, where we're going to substitute in vy here, and we end up with y essentially equals 1/2 at squared plus v0y times some time t plus ay0. And this be another equation we use. And then also from acceleration equals v dv dx. I'm not going to put the integration up here, just put our end result. You're going to end up with I'm going to put the integration up, I guess. And actually, we want to use dv dy here because we're only looking in the y direction. But so we'll integrate from the initial velocity to final velocity, and from our initial value of y to our final value y. And this will result in this relationship, and none of these should surprise anyone. So those are the kinematics of our behavior in the y direction. And then we'll split this up and look at the behavior in the x direction. And it's going to just result in simplified equations from above, because we're going to have a situation where acceleration equals 0, so your velocity in the x direction is going to equal your initial velocity in the x direction, because if you look up here at the equation, when a equals 0, the velocity equals the initial velocity. But in the case down below, you would use the relationships for x instead of y. And then our position, x equals the velocity in the x direction times time plus x naught. Again, the acceleration term drops out. So you end up with a constant velocity in the x direction and a velocity in the y direction modified by acceleration, which combine to make a final velocity. And the way you'll solve these problems, you're going to have certain values in these equations that are given, often as initial conditions, and you'll just solve for whatever you need based on those. So here's an example problem we want to solve. What is the height of the chip launched out of this wood chipper after 20 feet, after it is headed 20 feet, if it's launched at 25 feet per second? So let's use the method we just described above to solve this problem. So here we have an initial displacement of 4 feet in the y direction. We're going to have a final in the x direction of 20 feet. We're interested in the height here. So this will be y final. Actually, let's call this just y0 and xf. And then we're looking for a y final here. We've got an initial velocity of 25 feet per second. And that's about it. So we can break this 25 feet per second into horizontal and vertical components, and we can approach this with horizontal vertical kinematics here. So in the y direction, let's look at the velocity in the y direction, which is at plus vy0. So we're looking at minus 32.2 feet per second squared times time plus velocity y0 and if we integrate that, we're going to end up with a y equals 1/2 at squared plus vy, initial velocity in the y direction, times t, plus our initial displacement y0. And let's put in some numbers. So minus 32.2 over 2 times t squared plus 25 is our initial velocity. Sine of 30 degrees t, and then plus 4. So this y is essentially our y final. Well, we need to determine what t is, how long it takes for this to get that far. That's one way to solve this problem. So let's do that. So we can use the kinematics of the x direction to determine how long it takes to move across this 20-foot span. And so if we look at our relationship solved along the x direction, so this would have come from so solving this integral with a constant acceleration and then setting the acceleration equal to 0, and then solving this integral dt equals v, except this isn't a y, this is an x. In the x direction, we end up with this, and again here, this is 0. And then since we're starting at 0, this is also 0. So really what we're looking at here again is x equals the velocity in the x direction times t, and the velocity in the x direction for this is the cosine of equals 25 feet per second, if I'm not mistaken, 25 feet per second times t, and the distance we're moving is 20 feet, so we can solve for t. Therefore, the time it takes to get that 20 feet, so the time it takes for us to go from here to here, is less than a second. So it's 0.93238 seconds. So now I can take this t and I can substitute it up here and figure out what y is. So we just substitute in 0.9238 where needed, here and here, here and here, and y, the height, equals 1.81 feet. Then our result. So we land here at 1.81 feet, which is actually lower than the position that we fired out of our wood chip cannon, I guess, or our wood chipper. But our datum line was the base of this wood chipper, so 1.81 feet.